Now we can introduce the first isomorphic theorem, isomorphism theorem. First isomorphism theorem. So as usual, suppose we have a homomorphism from R to S. R and S are rings. That is also epimorphism. Epi. Okay. Then also kernel of F is K. Okay. Then we have a isomorphism. Then R by K. So this is called just like factor groups. We call this. This is a ring, as we have seen before. And this ring is called a factor ring. This is isomorphic to S. Okay, let's prove this. First of all, this kernel K is an ideal. And so we have an epimorphism from R to, so let's write like this, epimorphism to the factor ring R by K. So we have, let's summarize in a diagram. We have epimorphism from R to S. And we have another epimorphism from R to R by K. Okay, now we define a mapping from R by K to S. That is called H by the following. So H plus K. So since R by K is a factor ring, its elements are of this form. X plus K is defined to be f of x. Okay. And so we have seen this situation before in the first isomorphism theorem for groups. Okay, so as an additive group, this if we regard R as an additive group, we know that this mapping H is isomorphic. It's an isomorphism from R by K regarded as a group to S regarded as a group. Okay, so this is actually an isomorphism as we have seen before in the first isomorphism theorem for groups. Okay, what we need to show is that this H is also a ring isomorphism. To that, we need to show that this H preserves multiplication. So that's all we need to show really. So H x plus k, y plus k. So if we calculate this part, by the definition of multiplication between these two cosets, this is xy plus k. And by the definition of H, this is equal to f of xy. But F is a group isomorphism, homomorphism. So this is split into f of x and f of y. But by the definition of H, this is equal to h of x plus k and h of y plus k. So therefore, H is a ring homomorphism. Which is also isomorphic. Therefore, R K is isomorphic to S, and we are done. Next, we would like to prove the second isomorphism theorem, but before that, let us introduce one little lemma without a proof. So let R be a ring, and S be a subring of R, and I be an ideal of R. And then if we define S plus I by x plus A, where x is element of S and A is an element of I, is a subring of R, and I cap S is an ideal of S. Okay, so this is a little bit involved. So let me explain this in terms of a diagram. So first of all, we have a ring R, and S is a subring. So it's a subring. And I is an ideal of R. So we write like this with a curve here, because S and I are both subsets of R. Okay? And then we have, let's consider I cap S first. So S cap I, so let's write like this, and this is also of course a subset of S and a subset of I. And we are saying I cap S is an ideal of S, so this is an ideal. And we have S plus I here, so S plus I, and we can have a mapping from embedding from S and from I. And S plus I is it says a subring of R. It's a subring of R. So we have this arrow, subring. So here's the situation. So we have this as a subring and this as an ideal of S. Okay, so what's given is R, S, and I. I is ideal, S is a subring of R. So try to prove this lemma. Now we introduce the second isomorphism theorem. Okay, the setting is the same as the previous lemma, and what this says is that, so using all these things, what this second isomorphism theorem says is that the factoring of S plus I by I is isomorphic to the factoring of S by S cap I. Okay, so that's what it is. So so let's see. The factoring of S by S cap I and the factoring of S plus I by I. So these things are isomorphic. So let's prove this. And first of all, let us define mapping. P from S to the factor group S plus I by I by P of X is equal to X plus I. Now, all the elements of S plus I are of the form of X plus A, where X is an element of S and A is an element of I. So if we take the factorized by I, then elements of this factor ring is of the form of this X plus I, where X is an element of S. Then this P is an epimorphism. Epi. Okay, then if let K be the kernel of P, then by the first isomorphism theorem, we have S by K is isomorphic to S plus K, I. So we have this situation, S and S plus I over I, and we have isomorphism S by K, and we have an isomorphism here. So this is the result of the first isomorphism theorem. Now note that this kernel of K is defined as all elements of X that are, let's see, S plus I, such that P of X is equal to I. But that is actually equal to not just I, but some of the elements of S may overlap with I. So we should take this as the kernel. So the kernel of, sorry, this is not K, it's P. Kernel of P, its mapping P is, should be this. Okay, so replacing K with this, we have S by S cap I isomorphic to S plus I over I. So we are done.